Hey there, let's talk about kinematics with integrals. Kinematics is a topic that we're already familiar with, and we know the relationship between the position, velocity, and acceleration functions as SVA, where when we go down the line, we are taking the derivative to get to the next thing. But now that we know all about integrals, we could possibly go backwards down the line. Let's say we're given the acceleration function and we want to find the velocity function. We would take the integral of the acceleration function to get to the velocity function. If we were given the velocity function and we wanted to get to the position function, we would do the same thing. Okay. And don't forget that when you have an indefinite integral, you have to add on that plus c. So you're going to get some initial condition or boundary problems with these. We'll go over those later on, though. So remember that kinematics in general, right? This is something's motion along a line. Let's say an object's motion along a line, a particle's motion along a line, right? So this is the origin. And the particle is starting there. And then he's going to move to the right. Then he turns around, he changes direction, comes back. Oh, he passes through the origin again, heads to the left, then ends up somewhere here, let's say. Okay. Distance traveled is going to be the particle's distance here, plus the particle's distance here, plus the particle's distance here. Versus displacement. Remember, displacement, all we care about is how many units to the left of the origin this guy ended up, right? So we would say like maybe his total displacement was -4 units or something like that. The negative tells us that we are to the left of the origin. Whereas if it was a positive, they would tell us that we are right of the origin. But in total distance traveled, this counts as distance traveled, this counts as distance traveled, and this counts as distance traveled. So we have to account for the fact that movement is movement, and it needs to be accounted for. So when we're calculating distance traveled with integrals, we integrate velocity to help us find the distance traveled. However, distance traveled considers all changes in displacement, even negative changes or going backwards, right? So even when this guy was heading in the backwards or negative direction, this still counts as motion. He probably went like, I don't know, 15 units or something like that over the course of that movement. So we're not just going to totally discount that because it was to the left. So distance can be found with the area under a velocity curve, but we use absolute value to deal with backwards movement. When we're calculating these by hand, absolute value is pretty tricky to do. So we are going to still split up the integral between each root, but then we're going to change any negative areas to positive by just subtracting the negative areas. That helps us move away from doing absolute value by hand, okay? So let's look at example number 1. A particle has a velocity function v of t equals 1 minus 2t centimeters per second. Find the distance traveled. So we're thinking the total length of the path, right? That's in the positive or the negative direction in the first second of motion. So I already have the sketch here to just save a little bit of time, but we started when time is 0, and then this guy started up here and moved all the way down to here when time was equal to 1. So if you'll notice, this area right here below the x-axis is going to be negative. So in order to account for that, when we're setting up our integral, we are going to look and see, okay, so from 0 to 0, we set this up from 0 to the first root. And then we have the function inside. And then we're going to subtract the negative portion because that will get our sign correct for us. So we're going to go from 0.5 to 1 is our bounds, and then we're still using the same function here. Okay, so then we're going to integrate. We would have t minus t squared, and we're integrating that from 0 to 0.5. And then we're subtracting this whole piece here, which would be the same thing, t minus t squared. And then this time it's from 0.5 to 1. Okay, so we would evaluate the function at the upper bound minus the lower bound, and then subtract the same thing for back here. So we would get 0.5 minus 0.5 squared minus, here it would be 0. This would just be 0. Okay, so that's our first piece. And then we have minus, and then in here we're going to have 1 minus 1 squared minus the second piece, which is going to be 0.5 minus 0.5 squared. All right, lots of parentheses going on, but we can do this by hand. All right, 0.5 minus 0.25 is going to give me 0.25 minus 0. He disappears. Minus, this is going to be 0 minus the same thing here. This is going to be 0.25. So we have minus a minus 0.25. This would turn into 0.25 plus 0.25. This is going to give us a total distance traveled of 0.5 centimeters. So let's go ahead and check that on our calculator. Remember, when we did this by hand, we subtracted the negative area on the graph in order to avoid having to use absolute value by hand. When we're typing it into the calculator, we are going to put those absolute value bars in though, and we got the same answer, so we good. All right. Now we are using graphs to find total distance traveled. Okay, so instead of being given just the function and we have to just figure it out, sometimes they'll give you a picture. So the velocity time graph for a train journey is illustrated in the graph alongside. We have to find the total distance traveled by the train. So we need to find the area under this curve in order to find, this is just kilometers per hour, the total distance traveled. So we know that area is going to be equal to